Hi everyone, once again, welcome all of you to the to Price Webinar series. And today we have with us Professor Sergei Kalinin, who is joining us from University of Tennessee, Knoxville. Professor Kalinin is a Western Fulton Chair Professor at the University of Tennessee. And in 2022 to 2023, he has also been serving as a principal scientist at Amazon Special Projects. Before that, he spent 20 years at Oak Ridge National Labs, where he was a corporate fellow and group leader at the Center of Nanophase Material Sciences. He received his MS degree from Moscow State University in 1998 and PhD from University of Pennsylvania in 2002. His research focuses on the applications of machine learning and artificial intelligence methods in material synthesis, discovery and optimization, automated experiment and autonomous imaging and characterization workflows in scanning, transmission, electron microscopy, and the like. As a part of his professional services, he organized many professional conferences and workshops at APS and ABS. For 15 years, he also organized workshop series in PFM and served on multiple editorial boards, including Nature Computational Materials, Journal Applied Physics, and Applied Physics Letters. Over to you, Professor Kalinin, for the rest of the talk. Thank you.
Thank you very much for the introduction. It's a great pleasure to share some of the things and concepts that we have been working on for the last several years. I was also delighted to hear from Professor Jagtap that one of my students in my class has now joined the VPI. So this is kind of great to hear, and hopefully the background that he get can contribute to the success of the group and the university. So today I'm going to talk about some of the concepts beyond building the autonomous material synthesis and characterization workflow. So this is fairly a mouthful. So let me explain kind of what is that we try to accomplish and why is it necessary. So we can start with the statement that world is ultimately a material opportunity, right? So the scientific community got excited about the machine learning in around 2006. So within the paper by the Gerd Sider came out talking about the predicting crystal structure by merging data mining with the quantum mechanics. So obviously there was some work on the combination of machine learning and computation before, but this paper was an inflection point when broad community realized that there is a power in combining the predictive modeling and machine learning. But ultimately, we know that in order to make things real, we actually have to make them. So prediction is great, but ultimately we talk about the real world technologies, whether it is electronics, solar materials, the conductive polymers, or even some futuristic materials like materials for the space elevator to take us to the orbit. So for things to become real, we of course have to have the right functionality, but right functionality in the synthesized material, not in the theoretical construct. We have to have manufacturability, so we need to be able to make them with the technology that we have rather than the whatever future vision of atomic assemblers. And we also have to think about the costs, right? So we can make perfect solar cell materials, but for solar energy to be economically viable, the cost has to be controlled. So in principle, this being said, we also know that material science cannot change overnight. So all experimental sciences are usually fairly inertial and change slowly. But what's happening now comes very, very close. So maybe not overnight, maybe on the time scale of 2-3 years, but the changes that are undergoing now are literally tectonic or disruptive, depending on whether you want to use the kind of Silicon Valley type of terminology. And I think that the previous time of change was in early 80s, when the personal computers start to appear. So if you look at the history a little bit, things like Word, Origin, PowerPoint, they were invented in the early 80s, along with the personal computers. So of course, at that time, things were changing fairly slow because computers could be fabricated only at finite rates. They were super expensive. So that adoption of personal computers changed quite a lot of time. So let's say a decade. So we were limited by production. Now we are not limited by production anymore. Now we are limited by how fast we can learn. So because the ML tools appear essentially overnight. So what limits us is learning how to use them for material-specific problems. Then quoting the statement from Oppenheimer, the movie, theory can only get you so far, and machine learning can only get you so far. We know that the very high valuations on the AI now, so they're based on the expectation that AI will create new businesses like Amazon, new Googles, new Amazons, new Facebooks, or that AI will create the new materials, drug targets, and so on and so forth. I don't think it is going to happen in quite that form because the success of the companies like Amazon and Lyft or Uber or Airbnb had been predicated on the fact that we used IT and AI in order to leverage existing ecosystems, transport, extra building capacity, mail, and so on and so forth. So we are not going to be able to do it again. So when we try to propose to use AI to make new molecules or new materials, we actually try to reverse the trend and use the existing AI ecosystem in order to make new opportunities in the material world, which is always much more complicated. And in order to bring this process to fruition, at some point, we need to cross the boundary from predicting stuff to actually making stuff. And the question is, what's the state of the art here? So as I mentioned in the beginning, you can argue that the AI revolution started from 2006 when CIDR have proposed the combination of data mining and quantum modeling. And by now, this is a very well-established field. So there are multiple papers coming from organizations such as Google, Microsoft, individual startups, which basically all try to solve the predictive problem. You start with some search space, you perform calculations, typically with the progressive complexity veracity, you come up with a small number of the candidate materials, and then it's time for validation. So these candidate materials are given to the experimentalists, and suppose the experimentalists need to make them and test them. So by now, this is 95, if not 99% of the effort in the field. So what's the problem here? The problem is that for many areas, experimental validation is science in itself. So predicting drug target and small molecule and realizing and testing it is a very different thing. And by now, if we invest more and more effort into the prediction, we are not going to accomplish much because the limiting stage is testing. And the second part is that this scheme lacks the feedback. So ultimately, we run the experiments because ultimately the new knowledge is generated only from experiments. And once we have it, we need to include this new knowledge into the theoretical model. So by now, this is not done, and it's understandable why, because we, of course, are not going to change DFT or MD based on the results of single experiment. We typically build those models over integrated experimental results over a very large community. But if we want to realize the AI scientists, we actually need to learn from a single experiment somehow. So anyway, another very important thing about the theory is that in 2006, Amazon Web Services formed. And what it meant is that the activation barrier to start high throughput computing become very low. So before that, you want to do serious computation, you need to build a cluster. After that, if you have the account with the money, you can buy the EC2 from Amazon, and you can run as many computational workflows as you want. You can be in Alaska, no slope for that matter, doesn't matter. So what happens in experiments? So in experiments, the state of the art is what is called myopic Bayesian optimization method. So it's easy to illustrate using the simple parameter space. So let's say I want to explore some phase diagram. So the way I explore it, I pick some composition, so some point in this phase diagram. I synthesize the material from this point. Then I take a physical measurement. For example, I measure a spectrum. So here, a very important step is that once I've taken a measurement, I need to figure out what is that about the measurement that I care about. For example, the position of the peak, let's say band gap, the height of the peak, the PL intensity or quantum efficiency. So I need to define something that I actually care about. And sometimes it's obvious. Sometimes it can be something more subtle. For example, I can say that this small peaks over here is something that is indicative of the phase instability of the material. And rather than trying to do anything about these peaks, I want to actually minimize those peaks. So the choice of this optimization function can be actually fairly complicated and very domain specific. But anyway, if I figure out what I care about, then what I do is I create what is called the surrogate model. So basically, a surrogate model tries to do is to, given the measurements in small number of points, it tries to interpolate the function over the whole space. And it tries to interpolate not only the function, but the function uncertainty. And then based on the function prediction and function uncertainty, I formulate my search policy. So this is called an acquisition function. Roughly, it allows me to tailor exploration exploitation balance. I can say that I want to go for optimization, or I can say that, you know what, there are places in this phase diagram where I have no clue what goes on. I want to explore things first that I don't quite understand. And of course, the way that you choose exploration exploitation balance depends on what is your experimental time, right? So if you have to finish things in 3 iterations, you will go for greedy algorithms. If you want to, if you have enough time, you can spend some time on fundamental studies, kind of go exploratory. So this is where we are. So once I joined University of Tennessee 2 years ago, after my year in Amazon and 20 years in Oak Ridge before then, University of Tennessee actually had a fairly established record in automated and high throughput experimentation. So some of my colleagues in material science department worked on the combinatorial synthesis for more than 15 years, both for material exploration and for processing. My other colleagues work on the automated robotic synthesis. So University of Tennessee was actually one of the first places to start the autonomous experimentation synthesis in 2019. So it started with one of the first commercial OpenTron robots. So now we have the filmmaking robot sitting in the glove box. So you can see how it basically creates the, takes the sample, picks some solution, drops the solution on the plate, and then does drop casting, and then you have a new film prepared inside the glove box. So once I joined the UT, my work is aligned more with the characterization side. So my group works on building the autonomous workflows for scanning probe microscopy. So we have the instrument that sends the data to the University of Tennessee supercomputer. The data is analyzed, and then we return the control commands back to the instrument. So in collaboration with my colleagues in electron microscopy, we build the same capability for electron microscopy. So I think that by now, University of Tennessee is the only academic center that has this direct integration between the microscopes and supercomputing. And we started to work with our colleagues to do the same type of developments for things like nanoindentation. So you can see that here the nanoindentation is performed not on the regular grid, but on the pre-selected locations that the algorithm decided are interesting. And what's cool is that the types of algorithms that work for SPM, STEM, or nanoindentation, these are pretty much the same algorithm. So it's just a question of what you want to explore. And we also do some other cool things like using electron microscope as the 3D printer. So this is crystalline silicon, this is amorphous silicon. You can see that we can use electron beam in order to essentially 3D print atomic silicon, atomic plane by atomic plane. So anyway, this is what we do. And one of the things that was very, very clear is that, okay, we can have human-run tools, we can have autonomous tools. But the key question here is how can we make all these capabilities work together? So why is it difficult? It is difficult because this example of the feedback loop for Bayesian optimization that I've shown you, yes, this is the state of the art, but unfortunately, this is absolutely not enough to make the real world labs work. So in some sense, myopic loop is making one type of decision over and over again. But if you run a lab, your decision making is much more complicated. So for example, if we make the lab for synthesis of the hybrid perovskites, you start with some reagents. You can use a robot to make microcrystals. You can use another robot to make films. You can grow crystals. You can study them by different properties like optics, by the cathodoluminescence, XPS. You can make devices out of microcrystals or the films or even single crystals. But the type of decision that you make is much more complicated than simple optimization. So for example, if I want to use my microcrystal library to choose the sample for thin film crystals, that's okay. That's a relatively simple data-driven decision. But if I want to use the cathodoluminescence data in order to choose the right compositions, or if I want to change my processing based on the results of XPS, this is a very complex decision. So this is not what simple machine learning can do. So the real labs always have the multiple levels of decision making. We always have multiple iterative cycles. And to be honest, the best way to make effective decisions is to understand the science of what goes on. So if we know physics, we actually understand what to do. Problem is that generally we don't understand physics. We actually want to learn it. And it turns out that this is absolutely universal. This is actually absolutely universal for all sciences in general. We can represent the scientific progress like this. So here we are on the material side. So we just make things in the lab and study them. That's relatively fast. Then we move to the device prototypes. Then we create a product. So here, the value is propagated from right to left. So the economic value is generated when we have a product, not when we're in the lab. The functional knowledge usually propagates left to right. We typically learn things by doing fundamental exploration. The problem is that here things can be done relatively fast and cheap, and here things are very, very slow. So if commercializing some product takes years, there is no way we can use a normal Bayesian optimization to do it multiple times. So we need to have a far more effective strategies. And that's exactly the challenge for the machine learning. So we deal with the scientific data, which is high dimensional and usually represents different aspects of material. The value can be understood only down the line, meaning in the future. And typically we have to couple this multiple exploration loops. And then we can ask a provocative question is machine learning enough to do that? So imagine that we have this triangle. So one corner is the big data methods. So DCNNs, large language models, what's not. So this corner is physics, analytical theory, computational methods, what's not. It's not obviously discrete things. There is a continuum of methods, for example, structured Gaussian process, physics-informed neural networks, which combine both the data-driven and physics-driven aspect. Then you may ask, what's in this corner? And I pose that the third corner would be what we call rewards, meaning what is that we want to accomplish. So it can be anything. It can be minimizing climate change. It can be developing better storage material. It can be making a lot of money. The common thing about this is that there is a big gap between the physics and machine learning and the specific rewards. So the rewards in physics and ML itself are usually much simpler. So for example, the typical reward function in a database method is the loss function that we minimize when we train a network. So in physics, it's a little bit more complicated, but generally we believe that the good physical model is the one that allows for parsimonious representation of our system and the one that has a good predictive power, and those two somehow balanced. So obviously, we cannot train the neural network to discover a better storage material. We need to create a loss function that we expect will lead us to the better storage materials. And of course, there are a lot of things in between, right? So, for example, in manufacturing, the reward functions are complex. Material prediction, they're usually much easier. So there is actually a spectrum of rewards from very simple that we already use to very complex that we don't even know how to approach, but there are also a lot of things in between. So the question is it a kind of fundamentally new word, or is it just something that machine learning community is actually familiar with? And interestingly enough, if you read the regular books on the kind of techniques of the machine learning, you are not going to find something like this formulated explicitly. But if you read the book by Peter Norvig and Stuart Russell, so obviously Norvig, of all people, Norvig actually knows quite a lot about machine learning, you will find a very interesting statement in the introduction. And this statement is that somewhat remarkably, almost all AI research until very recently has assumed that the performance measure can be exactly and correctly specified in the form of utility or reward function. So my point is that there is a tremendous amount of effort and expertise and accomplishment and developed tools sitting in the pure AI world, but the difficulty in applying AI for the real world problem is by now, first and foremost, the problem of defining the right reward function. If the reward function is defined, then any problem is optimization problem, and we actually know how to solve optimization problems remarkably well. And in fact, if you look at what the people are doing, we're talking about with all these things about AI risk and whatever, essentially, this is the problem of the reward function misalignment. Now, so obviously I have no clue how to solve this problem in general, but I can show you how this principle actually works for microscopy, simply because microscopy is something that I worked with for quite a while. So my first papers where we talk about combining ML and microscopy, so towards the thinking microscope, was published 15 years ago. And after that, I've done a lot of work on combining neural networks for physics learning, data analytics, and so on and so forth. So starting from about 8 years ago, or actually 10 years ago, it stopped being a hobby and it became a profession. And for the last 7 years, I have been working on the developing of the methods for automated experiment in microscopy. So let me show you how this reward concept, so where it came from, and how it can be made useful. So let's assume that you want to build a better microscope. So it turns out that you can try to focus on improve energy resolution, minimize beam damage, improve spatial resolution, and so on and so forth. These developments are agnostic of material. So any material will benefit from this type of capabilities. But this is ultimately not what the material scientist who uses the microscope want to accomplish. Ultimately, you don't kind of, I mean, you know that having microscope with the better resolution is better, but your goal is not to improve microscope resolution. Your goal is to run a microscope experiment to solve real world problem. For example, make better material, improve battery materials, find material for removing methane from atmosphere or reduce corrosion. So, or maybe learn physics, but that's your goal, not building the microscope. And what we need to do is to basically, the way we think about this type of things is that we implicitly create the hierarchy of rewards and objectives, going from what is our overall goal to something that we can do in the lab. So for example, if we want to reduce global warming, we know that one of the ways for doing is to make cheap materials for grid storage. And in order to do that, we need to understand the mechanisms for degradation. And if it is your day in the lab, you try to run the electrochemical reaction in situ stem, and your measure of success is something that you can learn during this day. But obviously not this, and not this. So with this being said, we can represent working on the instrument as a workflow. So what is workflow? So I'm sitting in front of the instrument, I can type in the commands, And generally, these commands are relatively simple. So at least for microscopy, they're simple. I can tune my instrument. I can zoom in on some specific region. I can zoom out. I can zoom in and zoom out more. I can take spectral measurements. So basically, we can, this is what human operator does. This is how we can represent it on the level of the instrument. So this is a set of operations defined in the minimal control language. But the important thing is that the human makes these decisions informed by the prior knowledge of the system and in pursuance of certain objectives and rewards of the experiment. The same person sitting in front of the microscope, if we have the same sample in the same microscope and it's run by different people, then they will choose with the different objectives, they will structure the experiment totally differently. So with this being said, how can machine learning factor in microscopy experiment? And it turns out that what we need to look at is what role machine learning agent plays in the decision making. So for example, if we run the experiment and then we go to our office to analyze the data, we can use machine learning here. And in fact, maybe 8 out of 16 years that I work in this field, that was the only thing we were doing. But we really cannot analyze the data and change the experiment because it's already done. So the second level of machine learning is when we use machine learning to analyze the data in real time. So in this case, decisions are still made and orchestrated by human, but machine learning helps to represent the data in a form that is amenable to human comprehension. So then the third level is when the machine learning agent directly controls the instrument. So we realize the automation, or if it is kind of goes on for some time, autonomy. And there are two more levels, which basically defines what we do to the data and whether we have a feedback from ML agent, not only to the experiment, but also to the things like sample prep and so on and so forth. But we are not going to talk about it. So then if we want to realize the third level of instrument operation, what we have to do is to represent the instrument operation as the workflow, and the machine learning should basically implement it. So it can be done by providing the fixed policies, meaning that we tell in advance the instrument what to do, as essentially as a lookup table, or we can specify the rewards, and then microscope learns itself what experiment to write. So the reward can be dense, meaning that we provide it on each step. So this is myopic workflows like the Bayesian one that I showed, or the reward can be sparse, and then we somehow need to, meaning that it's available only in the end of experiment, and then we need to have some effective strategies to accomplish it. Now, if we look at the microscopy from this perspective, you can ask a question. So what are the reward functions in imaging? And there is a kind of well-known principle in physics that if you come up with a new theory, you need to show two things. One thing is that everything you have done before has to be explainable in terms of this new theory. And the second thing, the new theory has to allow doing things that have not been possible before. So it has to allow you to do new stuff. So it turns out that if we focus on the reward functions, then both conditions are satisfied. So first of all, everything that have been done by our group and all other groups in the world who work on the automated experimentation, and actually also human-driven experimentation, can be represented as a reward function. It can be something simple, like imaging optimization or physical law discovery. It can be something more complex, based on images or structure-property relationship, but there is always reward function. It is simply the case that when people publish the paper, no matter what the paper is about, you can read it and you will be able to figure out what was their definition of, what was their measure of success. So let me illustrate the example of the reward function, which is related to physics discovery. So notice that most of the time we need to combine synthesis, microscopy, and multiple other tools to learn physics. So there are not that many physical phenomena that can be learned only in microscope. But it turns out that there are some, and it happens to be the case that for about 25 years, I worked on the problems related to the tip-induced phase transitions in ferroelectric materials. So basically, ferroelectrics can store information as polarization. Polarization can be up or down. We can use microscope in order to switch this polarization. So this is physics done only within the microscope. So if we analyze the system, we can say that the formation of the ferroelectric domain can be limited by thermodynamics, or it can be limited by the pinning of the wall in the random potential, or it can be limited by the charge injection of the tip surface junction. So these are our alternative hypotheses. Then we build a machine learning scheme when we define our parameter space, we take the measurement, then we have a set of hypotheses, and basically our machine learning algorithm basically tries to update the hypothesis given the experimental data, and it also plans the next experiment, giving a preference to the hypothesis which most likely is correct. So think about it this way. Imagine that you have one instrument, you have 4 graduate students, all of them have the concept of what is the right next experiment to do. So you let the one who tends to be right more often to try more often. So for those that have low probability of success, you give them opportunity to try from time to time just to make sure that they come up with interesting and new ideas. But generally, you believe that if the hypothesis is right, then it is most predictive. So this is
Professor, just one question. So
sure.
in your last slide, basically, do we in the loop, do we need a human interference, or without?
Not in this one. So the human was required to formulate the hypothesis, so we did it at the time when there was no large language model, so it was human-based hypothesis space. But once they're defined, there is no human in the loop here. So this is kind of how it works.
Mhm.
So this is the experiment when we write the ferroelectric domain. So we apply the voltage of some bias and amplitude, and we draw a domain. Then we determine the domain size. This is our measurement. Then once the domain is measured, 2 things happen. So thing number 1 is that the microscope will reset the space, so it will erase the domains. So you see that it starts kind of deleting it. And at the same time, our algorithm will measure the domain size. So this is the same thing as this. And then the algorithm will start to plan next experiment. So this is how it looks of the kind of experimental trace analysis. So this is our parameter space. We have only bias, pulse, magnitude, and the lengths. And here you see how the algorithm tests different hypotheses. And then after a while, the hypothesis number 3 is the one that we believe or algorithm behaves is correct. So notice that people talk a lot about all these global visions of the AI-enabled scientists and kind of changing the world. 99% of this work comes from the top down, with the assumption that a sufficiently complex model can interact with the scientific kind of experimental scientific community in general, or within some big lab. But on the level of the individual tool, this is already done. So saying that it is in the future would be incorrect. It's already an accomplishment. So once I moved to UT, we basically build the same type of interface between the Oxford instrument and the supercomputer. So now we are running on more complex experiments where, for example, we use the machine learning agent in order to map the phase diagram of the combinatorial library. So combinatorial library is essentially a sample where the concentration changes from one end to another. So it's a cross-section corresponding to certain phase diagrams. So it's ferroelectric here, non-ferroelectric here, and then there are some morphotropic phase boundary. So the purpose of our experiment is to find out what goes on. And what you see here, the animation will work. Sorry, okay, so this should be an animation, but somehow it's not working. So this is already the experiment. So in this case, we have to do much more than one operation. We have to tune the instrument. We have to kind of ensure that we look at the optical signal and avoid bad regions. So in this case, the workflow is actually multi-step. But the end result was that we actually explored the physics of the Conda library. There are quite a lot of other things that we can do. So for example, this is the example of the mapping structure property relationship. This is automated tuning. This example is very simple computer vision experiment when we go through the sample, identify interesting microstructures and take measurements on these microstructures. So all these things can now be done. And as I mentioned, we can run the same type of experiments on the electron microscope. So we can take an image. The image is sent to the supercomputer. And in this case, so when we started to use deep learning, we build our own UNets. Now we typically can use something like SAM from Matter, so we can segment the particles. And then basically our algorithms start to take EDX diffraction and yields data one particle at a time. So you see we do measurement here, then we choose the next particle and take measurements on the next particle and so on and so forth. So this is kind of the case where we can even quantify what is the return on investment, because doing it manually, humans are slower. Doing it in a grid, we will waste a lot of microscope time taking the measurements where we don't need them to be. So in this case, this is a very effective way of doing stuff. So this being said, for a lot of
I have a quick question on the previous slide.
Sure.
So like the segmentation that basically so this problem that you're talking about, so you did mention about segmenting the grains, I believe, in the materials. So so does it involve a lot of human iterated data that you need to use for training these kind of models? Because I know from the biomedical side that when they are doing segmentation of CT scans or MRIs, they spend a lot of hours creating a data set, manually segmenting them so that they can train the model to do it automatically in the future. So do you also do something similar, or do you?
Yes and no. So you're absolutely correct that for medical problems or finding cats on the internet, segmentation is, creating the data sets is the crucial step. So for when we started, so this is our first use of the deep convolutional network, so 2016 for the microscopy data. We spent a lot of time figuring out what is the best way to create the training data sets. And there were problems moving from the post-acquisition analysis to the real-time sample analysis. So the same type of problems as people have in building the autonomous cars. So there are a lot of outliers. Obviously, the cost of outlier for the electron microscopy experiment is much lower than for the error in the autonomous car, but that was necessary. So currently, we of course can do the fine-tuning of the models. So we can of course do the fine-tuning of the models like SAM for our specific data set, but the key thing is that a lot of things can be now done using the foundational models like SAM. So for particle finding, microstructures that tend to work remarkably well. There are ways to tune it for specific application. But generally, in physical systems, we work with simpler cases than biology. So practically, we stopped doing the data labeling, but there are fields where it is necessary, and then there are fields where we can avoid doing that. Let me illustrate what type of alternative solutions we can develop based on the reward concepts. So, for example, the simplest problem is finding the atoms in the image, right? This is the basic segmentation of the atomically resolved data. So, for about 8 years, we did it with the UNets or something like this. Before then, we used the things like Laplacian of Gaussian. So why did we stop using Laplacian of Gaussian? Because it was brittle. You actually have to tune 4 parameters in order to tune it for specific data set. And then if the data generation condition change, then you need to tune it all over again. And then we asked ourselves a question. So maybe rather than having a supervised machine learning model, maybe we can do the automatic tuning of the Laplacian of Gaussian using the reward function. So what would be the reward functions? Very simple. If we look at the electron microscopy image, we expect how many atoms are within the image. And we expect, for example, what are the distances between the atoms. So we can use these parameters in the reward functions, so it's multi-objective optimization, and then we can find the optimal parameters of our Laplacian of Gaussian. So this is optimization in the 4-dimensional space corresponding to these parameters with the 2 reward functions. And this is the Pareto front that corresponds to the best balance between these reward functions. And it turns out that this approach works. And the beauty here that this approach is unsupervised. So the deep convolutional networks are supervised. They're obviously black box, and they're not terribly robust with respect to the auto-distribution shift. Once we use the reward-based optimization of the Laplacian of Gaussian, this is both robust and explainable and unsupervised. It just runs. All we define is the reward function. You see the example of my group and Professor Dusher group running this reward-based optimization over the electron microscope. And as you can see, it kind of works remarkably well. And then it turns out that we can actually use the same type of approach for solving fundamentally new problems. So let me show you an example of finding the radiation damage in the yttrium-barium copper oxide. So if you look at this image very carefully, you can see that in some places you can see this weak atoms, and in some places they're kind of distorted. So how can we find them using machine learning? So yes, we can do it by we can find them using the supervised ML, but creating the data set would take us a lot of time. So the question is, can we do it without a supervised ML? And the answer is yes. We generally have workflows that both us and many of our colleagues use for at least 15 years. And before then, there were on-off efforts, which works like this. You take with the image, you find the key points, for example, atoms. You create descriptors, for example, the square image, square patch centered on some atom. Then you do some form of dimensionality reduction. So the patch dimensionality is basically the number of pixels. So it can easily be like 600 dimensional object. Then you do some form of dimensionality reduction. So all the way from clustering to PCA, whatever. And then you visualize the resulting weights. And if you run something like this, you get an image which almost looks like I have found some radiation damage. You can clearly see the clusters. There is a trick. The trick is that this answer will very much depend on how I create descriptors, what type of transform I choose, or what type of dimensionality reduction I use. So if I change the parameters, I will still get an answer and it will be plausible. I just have no clue whether it is correct or not. And the same thing, I mean, that's a simple example, right? For many analysis workflows, the workflow can be much more complicated. They all follow the simple key point selection, transformation, dimensionality reduction, but it can be iterative. It can be come with the selection, so it becomes complicated. The worst thing about these workflows is that they are generally non-myopic. So the decision made here affects what happens here. So can the reward function concept help us? And it turns out that it can. All we have to do is to define the reward. So reward is basically, in this case, is how human will make a decision whether the results of analysis good or not. So this is human heuristic, combined with whatever we know about the physics in this case. And then if we do things this way, the workflow construction all of a sudden becomes an optimization problem. So you construct the workflow from parts, and then you optimize the parameters of individual iteration, but this is unsupervised process. And that's a big game changer, because sometimes it took years, it took months to build these workflows, and you never know whether you've done it right. And now it can be done in a supervised manner. And this is the example of how it works. So this is finding the ferroelectric domains. In this case, we know the ground truth, the polarization. So if we try to find this domain using simple clustering, we can get answers like this, we can get answers like this, we can get answers like this, depending on the descriptor shape. So this is clearly not right. We don't like it in physics when the phases are mixed. But this and this both look kind of plausible. So the question becomes, can we do it in the automated fashion? And the answer is yes. So if we define a reward function as the length of boundary, and the second reward function is how straight they are. So length should be minimal because boundary come with the free energy. And they want to be straight because they want to generally align with the crystallographic axis unless there is defects. Then we can optimize this workflow and get our operative run. So here, our boundaries look like this. Here, our boundaries look like this. We can say that, look, maybe this is the right solution. Or maybe this is some form of the phase separation that we don't know much about. And then it turns out that the reward concept allows us to take advantage of the automated experiment and kind of go to the next level of the instrumentation. So let me show you an experiment where we try to discover the regions with the maximum nonlinearity inside the material. So here it explores things more or less okay. Here it clearly wants to get stuck in the two locations. So what goes on? What happens is that in the conventional microscopy experiment, human does everything. So defines the experiment and executes it. In the simple experiment, our rewards are defined before and don't change. So sometimes it works, but sometimes it doesn't work. And then we realize that once we have the reward-based, once we have the classical myopic workflow, we can easily steer them by tuning the rewards dynamically. So I showed you the example of experiment when the reward was set just once, but it doesn't have to be this way. We can run the experiment where we define the reward dynamically based on the experiment progression. We also can tune the exploration-exploitation balance. And the reason why it is possible and in fact reasonably easy in experimental sciences is because humans have a culture of monitoring the experiment. Many other fields do not. But until now, all the equipment like this is run by humans. So we kind of can run the experiment and visualize the experiment progression. So this is the measurements as a function of time. We can see what type of microstructures the experiment explores. We can see how fast our machine learning model learns. So basically, these are monitoring functions. And then we can realize the workflows when the machine learning agent runs the microscope and human controls the reward functions for the machine learning agent. So this is implementation. So this is a video of the real ML agent controlling the instrument. So we didn't package it as a product, but it works. And then the human basically controls what type of targets the machine learning agent want to pursue. So either explore materials in the particles or outside of the particles. And then we started to realize that we are facing a very interesting transition. So current generation of the tools is that human sits in front of the microscope, introduces basic commands, and looks at what appears on the screen. So the tools that we built for the SPM, for STEM, now for non-indentation is a different type of tool. We have machine learning agent that issues the primitive commands and has access to the imaging and spectral data. So human, basically, of course, human can intervene, but generally human tries to affect the behavior of the machine learning agent, make it more or less curious, or change the reward. So the value gain here is that, so machine learning agent obviously can work much longer than human, but machine learning agent can also make decisions much faster than humans because for electron microscopy, microscope can work about 1,000 times faster then human can make decisions. Even though when I see when my kids play Ultimate Doom, start to have a feeling that maybe in their case it's 2.5 orders of magnitude, not 3 orders of magnitude. So nonetheless, we have a real gain here. So the second, and of course, ML agent can work with the large data volumes and so on and so forth. So what we are working on now is going to slightly more complex concept, and this is where our work start to merge with the effort of some of our colleagues that already work on the LLM-based for scientists. When we start to use LLM to effectively design the reward function, because sometimes, as I mentioned, reward function can be complex. It's not only a position of the peak, sometimes it's a small detail of the spectrum that actually matters. So humans can do it, but LLMs look like that they can do it as well. So I'm not going to go into the detail, but I can say that we need the reward concept if we want to integrate operation of more than one tool, because otherwise we need to compare what we learn. We need to use the reward concept if we want to have the theory in the loop type of experiments. And the interesting conclusion that we are coming to is that big data and associated big data infrastructure like foundational models is super useful, obviously, and sometimes sufficient. But it's sufficient in well-established fields with their plenty of real and downstream applications. So, for example, for medicine or biological images analysis, that's basically the only game in town. But if we go into more physics discovery, when people want to go where no one has gone before and find something new, big data cannot help us by definition, because for new areas, we simply don't have any data, not even big data. But the reward function approach basically allows us to extend the way humans do things into these new domains. So we need, of course, hypothesis making, like what to do, but reward function allows us to do things correctly. And it feels like for instrumentation, that would be a big part of moving forward. So, and as I mentioned, there are all kinds of interesting feedbacks. For example, LLMs seems to be a viable strategy to discover this probabilistic reward function. So that seems to work for some cases. So, and just to finalize, let me kind of speculate about where this may go in the future, right? So we know that science goes through the heavy disruption period, and it's already obvious that a lot of things that we are doing are done in the collaboration between the human agent and ChatGPT or whatever your favorite large language model is. So I use it pretty much for everything, so do my students. But for the time being, most of the work is kind of there is me and there is my digital assistant. So in the future, it's very clear that we have the right technologies for multiple humans and multiple machine learning agents to interact and solve the real world problems. And then if you start to look at the characters of how this type of interaction will look like, so it's collaborative environment between humans and AI. There is a role specialization. I can be good only the areas that I'm familiar with. So I'm familiar with ferroelectrics and microscopy. That means that my microscopy skill can be used for something else like polymers, but I personally don't know much about polymers. We have some objectives. So we want to accomplish something like make a better battery material. We have to interact dynamically and adapt. We obviously learn and grow. We have to make decisions in real time. A lot of what we are doing is automated task. We have to manage our resources, right? We have only so much computational power available to us or money in order to buy the reagents. We need to track progress towards our goals. So if you put all these elements together, we basically figure out that the labs of the future would be essentially something like a large role-playing game. And what's interesting is that after I come up with this concept, I explored whether it is real or not, and this type of work is being done. There are multiple examples like Galaxy Zoo or protein folding when the prototypical version of such interactions are already done. So future would be interesting, and I believe it can be a lot of fun. So this is, I would like to stop and would be happy to take questions.
Thank you, Professor Kalinin, for an amazing talk and a very informative session. So I'd like to request participants, if you have any questions, to kindly unmute yourself and ask any questions if you have at this point.
Yeah, I have a question actually, two questions. So first question is the large language models that you mentioned. Those are like the open models, or like some models that are trained specifically for or microscopy articles probably, and then you picking those and find the reward function you just mentioned in the PPTs. And the second question is the you mentioned from like experiment to interpretation of the entire process of the microscopy, there will be multiple steps, right? So how do you
Mhm.
define those steps for a ML agent? And in the part you mentioned about a policy, so what is that actually?
For the large language model, so we spend maybe a few months on playing with the large language models and using LangChain to take a model, train it on the archive, and kind of use it for specific problem. So generally, my observation was that the difficult part is not the LLM. So first of all, it's impossible to keep up with the rate of development of industry, and there is no need to do it. The idea is to learn how to adapt what they do to our problems. Second problem was that the difficult part is kind of transition from something that is relatively diffuse and expressed in the natural language to something that is actionable, and preferably something that is actionable and also comes with the uh, uh, which is stable in a sense that large language model uh, hallucinations don't affect our answers. So our solution for that was to formulate a request to the large language model to provide the output in the most confined form. So for example, if we want to calculate things based on the causal discovery, we basically tell it to formulate the answer as A affects B, B affects A, or they are unrelated. If we want to mine the literature for compounds, we want to properties, we just provide the schema of how we want to have the output. And if we want to do something else, then we are asked to output some segment of the knowledge graph. So we never published anything around it because for us it's not a goal, it's kind of the exploratory area. But this strategy seems to work. So then, of course, Google come up with a Notebook LM, and Notebook LM does wonderful job. Now they came up with a scientist, but I mean, I haven't played with it yet because I don't think it's commonly available. But in all cases, the problem is how to constrain the output of the LLM and the form that you can use and make it sufficiently narrow that when the LLM says something stupid, it doesn't affect that your core optimization algorithms work. So the second part with the reward function. So for the time being, that's an open area. So I believe that people who will solve the reward function problem, they essentially solve machine learning, which basically means that it will not be done. But this is just the direction with which nobody have actively worked. So a lot of communities, most notably reinforcement learning, they all are coming to conclusion that reward engineering is important. But in the scientific world, I mean, 2 years ago, most of the people don't even know what the reward is. It's just not a part of our dictionary. So by now, generally, people understand what is optimization function, and that's pretty much the same thing in reward, but we are not exploring, as a community, not exploring the reward functions yet. Given how fast the field is developing and that this is ultimately very amenable to LLMs, I will not be surprised that in 2 years from now, that would be one of the mainstreams of ML, or maybe not, who knows, we'll find out.
Yeah, and one other question that from like conducting the experiment to the final interpretation, there are the several steps. So how do you define those steps for a ML agent?
So this is a problem of kind of connecting the real to ideal type of stuff. So in case of scientific instrumentation, that's actually relatively straightforward because in scientific experiment, the operations that we can do are the operations allowed by the instrument. So in some sense, we don't even need to think about it. I mean, at least in the very beginning, we don't need to think about it. We can start with the operations amenable to the human operator, and then our goal is to kind of give the machine learning agent the API that allows to do this type of stuff. So in the future, I can envision the situation when the ML agents will come up with the beyond human operations, but that future is in the kind of considerably in the future simply because we don't even have the APIs for simplest thing at this point.
Yeah, okay, got it.
Thank you, Professor Professor Kalinin. If there is no question, then we can thanks Professor for this enlightening talk. By the way, we have one follow-up talk. If you are free, if you have time, you can feel free to stay.
Thank you. Appreciate it.
Yeah.
So I kind of have to move on to
I-
the other thing. Thank you very much for the invitation, and if you have further questions on, would love to connect directly.
Sure, definitely. Thank you, Professor. Bye.
Bye.
Donsub, are you there?
Yes, I am here.
Sorry, we are a bit late, 5 minutes.
Oh, no worries.
Yeah. So can you quickly share your slides so that we can see everything looks fine and we can talk in
Yes, 1 second. Share screen. Let me do full screen. Okay, can you see the slides?
Yes, that's perfect. Yeah.
Okay.
So Siddharth will introduce you and then you can start your talk. Siddharth?
Okay.
Yes, Professor. So once again, hi everyone. So this is the second session of the PySeminar series, and now I'd like to introduce as well as welcome Professor Donsub Rim, who's an assistant professor of mathematics at Washington University in St. Louis. He received his PhD at the University of Washington and has held postdoctoral and visiting positions at Columbia University, New York University, and Tohoku University. And today, Professor Rim will be talking to us on the title, FastLRNR and Sparse Physics-Informed Backpropagation. So over to you, Professor Rim, for the rest of the session. Thank you.
Okay, thank you. Thank you for the invitation. Thank you for the nice introduction. So I am on a early sabbatical this year. So confusingly, I am back at my institute where I got my PhD. So I'm both affiliated with Washington University and University of Washington, just to confuse everyone a little bit. Okay, so today I'm going to talk about FastLRNR and sparse physics-informed backpropagation. Let me quickly start by telling you what learners are. So learners are called short for low-rank neural representation, which is the family of neural networks, which I will explain. And then I'll talk about a meta-learning framework using the learners. And I'll get to the beef of the talk, which is, okay, what is a fast learner, which is a compressed version, compressed architecture of learners and backpropagation on these smaller versions of neural representations are what we call a sparse physics-informed backpropagation, which can run really fast. I'll show some numerical examples, and if time allows, I'll talk about some approximation theory that shows that if there's an efficient learner approximation to entropy solutions to scalar conservation laws. And let me acknowledge my collaborators. This is work joint with Woojin Cho, who was a graduate student at Yonsei University, and Kook-Jin Lee at Arizona State, No-Sung Park at KAIST, and Garrett Welper at University of Central Florida, and also thanks to Randy Levesque regarding the theoretical results. Okay, so let me first introduce what a learner is. I'm sure everybody in this audience is very well familiar with what feed-forward neural networks are. So let me just first set, but let me quickly set the notation. So given a depth L and a sequence of integers, sequence of natural numbers indicating the width of the network, we collect these spaces of all possible weight matrices with the right dimension and all the biases with the right dimension as this WL and V sub L. And a feed-forward neural network is commonly defined as an alternating concatenation of affine maps, which are, you to take your hidden state from the previous layer, multiply by a weight matrix and add a bias. These affine maps and nonlinear activation sigma, which are commonly taken to be either ReLUs or tanh functions. And you apply these scalar nonlinearities entry-wise from the incoming vector from the previous layer. So you take an affine map and apply a nonlinearity, an affine map, and nonlinearity. So this alternating concatenation results in a function, and that is a feed-forward neural network. And the parameters are all the collections of weight matrices, W, and all the collections of biases, B. So if you collect all the space of weights and biases in a Cartesian product, then you essentially define like all the possible instances of weights and biases. And so this WB containing like all the weights and biases of the right dimension, you can call this a collection and architecture. So you pick a weight, a specific instance of a sequence of weights and sequence of biases, and you have a fixed function in the form h of x parameterized by w and b. And these are, just a function. And neural networks with the spatial temporal inputs are often called implicit neural representations in computer vision literature. And it just means that your input is expected to be not very big. So if you have a spatial temporal input, maybe your spatial dimension is 2 to 3 dimensions, and your time dimension is 1, so 3 or 4 dimensional inputs. And if you're looking at plasma physical simulations, then you're really looking at 6 to 7 dimensional inputs, for example. Okay, so this is a feed-forward neural architecture, or is a low-rank neural representation. Well, we take this feed-forward architecture and we put in some assumptions. So let's say you take your weight matrix and factor it into 3 different weight matrices that has a SVD-like factorization. So we say that this WL, we're going to factor into 3 different weight parameters, U times sigma times V, and we say that this U has dimensions capital M times R, and this sigma is a diagonal matrix that's R by R. And this V transpose is again R times M. So, and we assume for simplicity, all the widths are sort of the same, except for the input and output dimensions. So let's say they're all equal to this capital M. So although capital M can be very large, thanks to this SVD-like factorization, we can say maybe R is very small. So although the dimensions of the multiplied product is still M by M, the number of parameters here is small. And of course, since this is a diagonal matrix in the middle, this sigma, it has an even less dimension. So just R parameters in the diagonal parameters. So to distinguish, we distinguish between the U and the V and the sigma. So what we'll do is we're going to call this U and V basis parameters and distinguish them from these diagonal entries of this middle matrix sigma. We're going to call those coefficient parameters. And they're going to play different roles in low-rank neural representations. Assuming that we have spatial temporal inputs, now we call this an INR. And this INR now depends on your choice of, the basis parameters U and V and the bias. And there is also these coefficient parameters S. And if you suppose that, okay, through some learning process, you learn U, V, and B, and then you fix them. We'll get to how we learn, we're proposing that we learn them. But once you fix U and V, then this middle parameter is all that's variable, this sigma. And there's only a few of these coefficient parameters compared to U and V. So once you fix that, U, V, and of course you also learn the bias and you fix them. So U, V, U star, V star, and B star. Now this whole thing it depends only on the variable S, the coefficient parameters. And then now you get a family of INRs, which this is what we call low-rank neural representation. So rather than being a single neural network, now we're talking about a family of neural networks that is parameterized just by the coefficient parameters S. So this S had...
I have one question. Sorry,
Okay.
I missed what is B here? Small b?
Small b is the bias.
Oh, okay.
Yeah.
Okay.
You can also factorize the bias. So we'll get to this later, but let's forget about the bias for a minute.
Okay.
And say the weight, somehow we're going to assume that the weight matrices W have this factorization structure.
Professor Rim, I have a question here. So
Okay.
you mentioned about the UL and BL, and you did mention that you're fixing those quantities. So if you have like L layers in your network, and if the number of neurons is varying between the layers, does it mean that you're going to have, like, for instance, a three-layered network with different number of neurons in each of the layers? Then do you have like three sets of U star, V star, and B star?
Okay. So the neurons you're mentioning are, the hidden states, right?
Yes.
So the number of neurons will still be the same. It'll still be M of all the internal layers.
Right.
If it's an INR, then the input is spatial temporal, so it's small dimensional. Output is also small dimensional. Like in pins, you
Right.
have a spatial function. The input is maybe, 2 or 3 dimensional. Output is 1 dimensional or 3 dimensional or something like that, right? So the
Right.
internal hidden states, those are going to be all capital M dimensional. So that could be very large. But
Okay,
what we're
I think I missed that because you are assuming that all these are having same number of neurons, right? Is that right?
That's right.
Okay,
But
okay.
this capital M could be very big.
Okay, thank you.
Yeah, it's just that this sigma is going to be small.
Don't just that actually, uh,
Mhm.
so basically when you create this SVD,
Yes,
you are creating this for each layer.
yes, each layer,
So,
all
so
of them. Yes.
basically your these U star, V star, and B star, they are basically you should also have L there.
Yeah, these are collections. So I'm going to say if I collect all of the U's, each
Mhm.
of them, we're going to call them basis
Collection.
parameters.
Okay. Okay.
Yeah, so this is like you can think of them as a tuple of, all the
Okay.
U's cells.
Okay. Got it. Yeah. Thank you.
Okay. Any other questions? Yeah, feel free to stop me at any point. So there's, the key point here is that this is still a very large neural network with lots of neurons or hidden states, except that you just assumed that these weight matrices have this SVD-like factorization. And if you kind of ignore the big matrices, U, V, and Bs, then it seems like it's a small dimensional system. So the dependence is small, but the neural network can be very big because with M can be still very large. I'll show you a diagram soon, but before I do that, no, actually the diagram is on the next slide. So I'll show you a simple example. For example, assume you have 3 layers and R is equal to 3. Right? Then you have, 2-dimensional input and 1-dimensional output. So your neural network looks like this. And your weight matrix here, W1 of this form, then there's this bias, which we call B1, and there's, the W2, which is the second weight, and then B2 is I guess, like the trivial bias, which is scalar. Okay, what I'm saying here is that, okay, I'm going to take this matrix, weight matrix W1, I'm going to assume that it has this sort of a factorized structure, right? And this is the U, and this is the V, and I'm going to say that these two matrices are going to be fixed, and this diagonal entries are going to be what's variable once U and V are fixed. Okay, and so I think the previous question about, okay, can you have a large number of neurons is corresponding to the fact that this can be a very tall matrix. That corresponds to the dimension M. But the rank is R is equal to 3, which means that you have, 3 diagonal entries. So you do that for both this weight and this other weight W2 as well. The bias B1 and B2 are going to be, they're going to be learned and fixed. Okay. And of course, you can also factorize the bias, which is what we do in theory. But throughout the first part of the talk, we will assume that the bias is just learned and fixed, like U and V. Okay, so this connects kind of nicely, in my view, to parametrized PDEs. Suppose you're solving a parametric partial differential equation, a PPDE, where you have some physical parameters mu, which is independent of the parameters of the neural network. And say that you're solving some differential equation that you notate by this differential equation n. So your n of u is equal to 0, and all of these depend on the physical parameter mu, and your boundary operator, which can also depend on mu. So b of mu u is also equal to 0. And if you recall that the learner weight has this factorization, we say that, okay, u and v are not going to depend on your physical parameter mu, but just the diagonal part is going to depend on the physical parameter. And so the basis parameters are going to be mu independent. And only the s's, which are the diagonal part of these, the factorization, is going to depend on mu, the physical parameters. So this u and v, they're supposed to contain some information that is global to the partial differential equation, the parametrized partial differential equation across all physical parameters mu. And we're going to say that, okay, the function has to change depend on mu, but that dependence is only going to come in through this diagonal matrix sigma. So we approximate the PPD.
Just one question. How this is affecting the representation capacity of the network? I mean, when you say that U and V are basically, you are learning those parameters, those matrices, and this is global, right? You are not, are you updating, are you learning the optimization process again, or just once learns it kept fixed?
It's learned in this framework. We're learning them once and for all. For E and B, they are learned once and fixed.
Okay.
Okay. Yes, it does affect, of course, the what do you say,
the representation capacity.
Yes, representation capacity, if you will, or approximation capacity. You are sort of restricting yourself a little bit. You do need some kind of you should have some low dimensional structure in your physical system that you suspect is there for for this to work, of course. Yeah, it is less general than fitting a different neural network for every problem, every parameter mu.
Thank you.
Okay. Yeah, feel free to stop me at any point. So now the goal is to approximate the PPD solution this way. You first, as the question was referring to, you first learn these global objects, U, V, and B, and you fix them. And then now you only, during this finding the solution to PPDE, you're really only concerned about finding these diagonal coefficient parameters that depend on you. So we're really trying to figure out what the dependence of the diagonal parameters, the coefficient parameters S, how it depends on the physical parameter mu. Okay, so how do we learn this? Well, we learned this U, V, and B, as I was referring to earlier, during this meta-learning phase. So we have two phases. We have a meta-learning phase during which you learn these global objects, U, V, and B, and you fix them. And then during the fine-tuning phase, given a new physical parameter, you try to find the coefficient parameters. And of course, as I was mentioning in the previous slide, these basis and bias parameters, they contain the information that is global to the PPD. And by the time that you finish the meta-learning phase, you're going to be able to do some kind of a data-driven prediction, a real-time prediction using, a hypernetwork. As I'll get to this soon. During the fine-tuning phase, what you do is if you're given a new parameter mu in your parameter domain, coefficient S is updated by, you can plug this learner into your parameterized PDE and solve the PPD using, for example, pins. And then you find the right coefficient parameters S. So given a new mu, you can plug everything into your PPD and then solve for the coefficient. So at the end of the meta-learning phase, you get like a data-driven guess, which is close to the solution, but you're not really sure that solution is exact. So what you could do is you could plug in this learner into your PDE and then fine-tune using pins, and then you get an updated and an improved solution that you're more certain that solves the PPD rather than being just a guess, just a prediction. And the main result of this talk is that the fine-tuning, the backpropagation operations during the fine-tuning stage can be made very quick, can be sped up. The complexity can be made to scale with the small dimension R only. That is the main, sorry, this order is right. The backprop complexity can be made to scale with R only. So you can accelerate the backprop operations you need during the fine-tuning phase. Okay. So what is the meta-learning framework? Well, it is a sort of a straightforward approach. So you add another hypernetwork, since we do not really know the relation between the physical parameter mu and the coefficient parameters S. You attach a smaller neural network that is fully connected, and you try to learn this neural network, which we call the hypernetwork. F hyper, that goes from the physical parameter domain to the coefficient parameters. And of course, this neural network also has its own set of parameters, which we call theta. So what we do is our meta network is, since we do not know what the dependence on S is, we plug in this F hyper as a proxy for S of mu. And we have given a physical parameter mu, this hypernetwork gives you these guesses for S1 to SL, and those are fed into our low-rank neural representations in the diagonal terms, if that makes sense. So we're attaching another neural network that goes from
I have a quick question. So when you're talking about the hyper network here, so what I understand is like so if it's like a 3-layered network, the prediction that you have would be a long vector with all these 3-layer representations stacked one after the other. And then once you have a new mu parameter, that mu parameter gives you a big long vector, and then you have to distribute it to the corresponding layers in your actual network. Am I right?
That's right. That's right.
Oh,
so
okay.
This F hyper network gives you, R times L. And for each layer, it's a long vector where each of the R components will correspond to one of the layers, and it'll go into the diagonal entries of the sigmas.
So does it mean that you need to have a separate set of data to train your F hyper, or does it or I don't know if you're discussing it. I think you'll be discussing it later, but is it like a combined training where both of these happen together, or is it
Yeah, we learn all of this together.
together? Okay.
All of this together, yes. Yeah, it's kind of there is a good analogy that you can make to operator learning, where you're not really learning just one PDE solution, but essentially a family of solutions all at once, right? And there are parts that are really only not dependent on the initial condition, for example, that you have that are fixed, and then you learn the coefficients, for example. So there is an analogy that you can make to that, but you learn all of this all at once during the meta-learning phase. Okay. Any other
So
questions?
here
Thank you.
the basically meta learning is it's a bi-level optimization, right? So it's outer loop where you are
Mm.
learning mu.
That's
Okay.
right. You can view it as like we don't really do two different levels separately. We learn it all at once. But yes, there is like two levels, two layers of things being learned. You're learning these U, V, and B, which are global,
Mm-hmm.
but you're also learning the sort of this outer loop level where you're learning, okay, maybe the physical parameters are mapping to the coefficients, which is, you can say is an outer loop. I'm not sure if that's exactly what you mean, but
Yeah, yeah. Yeah. Thank you.
yes, okay. Yes. Uh, All right. So how do we learn this? We plug this all into a pins loss, for example. Of course, it's not really necessarily tied to pins. It's just it's just a type of a neural network that we constructed that is amenable to learning in a data-driven way. But the most straightforward way to do this is to plug it into a pins loss. So you plug it into your parameter-dependent PDE and your parameter-dependent boundary conditions. And then, you have some spatial collocation points where you average this empirical loss. And you do it for, all of mu, right? So your spatial collocation points might be the same for all parameters mu, or they might be different. In our case, we fixed all the spatial points, and you sample also along the parameters mu. You learn the weight parameters, the basis parameters, U, V, and B, and you also learn the parameters to the hypernetwork. And recall that we had this SVD-like structure, and to remove redundant information in different columns of U, what we also do is we say that, okay, we would like these basis parameters for each of the layers to have orthogonal columns, or orthonormal columns, really. So you put in this orthogonality regularization term, which we call R-orth. So we say that this U and V, we would like them to have to be close to orthogonality as close to orthogonal as possible. So we say each UL transpose UL is close to the identity in the Frobenius norm, and we plug this orthogonality regularization term in our loss on top of the pins loss. Okay, and then we also say that we would like low dimensionality in our bases, which means that in the SVD, you would have singular values that decay. So in the next regularization term, we do sparsity promoting by saying that, okay, there must be some type of a decay rate for these coefficient parameters. So remember, these what's coming out of the F hyper is stacked entries of these coefficient parameters that go into the diagonal. And so we say that for each of these stacked diagonal terms that's coming out of the hypernetwork, we would like them to have a certain rate of decay. And this is one choice that we made. I'm sure there are other choices, but the reason that we chose this is somehow the learning procedure is it's dependent on what you choose. And you might think that, okay, if you choose, for example, the L1 norm for the coefficients, it might work, but that didn't turn out to train very well. So we had this choice where we are assuming that, okay, the coefficient parameters, so each stacked coefficient parameters that go into the diagonal, we would like to have a certain rate of decay. And this gamma is another hyperparameter that you can choose during the training process. Okay, so during the meta-learning phase, the bases and bias parameters and the hypernetwork parameters data is learned by minimizing this entire loss, the pins loss, and the orthogonality regularization, and the sparsity promoting regularization. Okay, so it's a little messy, but I think it has each of the part of the ingredients is inspired by wanting a low dimensional structure in your weight parameters. Okay, and during the fine-tuning phase, so once the meta training is over, you have U star, V star, and B star, so they're fixed. And then now the learner really only depends on S. I think I'm missing a B star here in between. So the learner really only depends on the coefficient parameters, so you'd like to learn these. And what you do is you sort of detach the hypernetwork. And then you only work with the learner architecture, which is, again, it really depends only on the diagonal coefficient parameters. And you plug this into a pins loss. However, now you don't really involve the hypernetwork during training. It's just that your hypernetwork kind of gives you a good initial guess to start this minimization. So you use given a new parameter mu, you want to learn the coefficient parameters S by plugging it into a pins loss, which just involves the PDE and minimizing the PDE and the boundary conditions. And then you take your initial guess as 0 from your hypernetwork mu. Okay. So, however, this backpropagation through using this the fine-tuning loss, every time you do a backpropagation, since our width m is very large, you do still have to do expensive calculations that scales with the m times r, and m can be pretty large. So the motivating question for this talk was the question, can backpropagation operation be made more efficient by exploiting the low rank structure? And let me first mention that there is a sort of in our first paper we were exploring, okay, what is this meta learning process good for, and compared to vanilla pins, which is of course which is now pretty old, it does learn parameterized systems a little better. So for parameterized systems, where if you directly try to solve it using pins, there's some known failure modes. But if you try to learn the entire system, you're kind of teaching it through you're teaching the easier and harder problems, easier and higher physical parameter values all at once. And therefore, it has an easier time of learning. For example, the pins, the vanilla pins, of course, fails for higher frequency Helmholtz equations. But if you learn everything at once up for all frequency parameters, then you are the accuracy you get from this meta-learned network is better. Of course, after fine tuning as well. Okay, but returning to the question of faster backpropagation, the learner architecture, actually the motivation for one of the motivations for deriving this low rank structure is precisely because of this. So if you look at one part of the learner architecture, you have this diagonal coefficient parameters S, and then you're multiplying this basis parameters UL. You pass it through the nonlinearity sigma, and then in the next layer, you're projecting back to VL plus transpose. And these you're assuming are low rank. So if all the hidden states were coming in from the previous layer and gets multiplied, then it means that by the time it passes through this basis parameter U, what's going to be passing through this nonlinearity, scalar nonlinearity sigma is going to be low rank. It's going to be in the span of the column of this U sub L or U super L. So if you have a low rank vector that belongs to a low dimensional space, and then if you're passing it through a scalar nonlinearity, it's well known that the output of this sigma can also be low rank. This is sort of well known in the model reduction community, and it's methods like empirical interpolation methods are able to approximate the outputs of although there's a nonlinearity in here, the outputs of this sigma UL times some small coefficient parameters very well by a low dimensional vector. And one way you can do this is by, subsampling the outputs. So you say that, okay, maybe only these rows, you only really need to know the outputs coming from these 4 rows. And then you can do a pre-calculation which compresses the output using, again, only 4 of these columns in the matrices of U. And then you come up with the smaller architecture that only scales with the very, very small reduced dimension that is commensurate with this dimension R sub L. So if we call that R hat L, which can be slightly larger than R sub L, because the output dimension of coming out of the sigma may be slightly larger than the input dimension. However, you come up with now a same type of an architecture where you replace this V by V hat, and you replace this U by U hat. And this U hat is a much smaller matrix. This V hat is also a much smaller matrix. Okay, so the idea is sort of, you're compressing the weights because you know that this learner architecture has this low rankness built into the weight matrices.
Professor Rim, I have a question on this one. So when you're talking about subsampling, you're mentioning that from the inside the nonlinearity, you're taking the subsampling maybe 4 rows, for instance, and outside the nonlinearity for the V metrics, you're sampling 4 columns. Now, in the beginning, the first slide, I think you had mentioned that the final product of the U times the diagonal times the V should respect the structure of your network. So which has M neurons per layer. So now when you're subsampling and when you're reducing it to RL cross RL cap cross RL cap, is it not is it like not respecting the structure of your actual network, or are you doing something?
Yes, that's the difference. We are taking a big network.
Okay.
We are compressing it. We're taking capital M to be small.
Right. Okay.
So yes, we are. It's sort of irreverent to say we're not respecting something, but
Okay.
yes, we are trying to.
No, yeah, all I meant by that word was that when you're backpropagating it, you will be keeping track of all the neurons in your network, right? So that's why. So then like your weight size of your weight metrics will also be equal to the size of your gradient metrics. Is that right to say?
That's right.
Yeah.
So
Yeah.
that's right. If you do, if you, in the original network, when you do backpropagation, I believe that is the key point. I think you're touching upon the key point. So when you do a backpropagation, you do need to go through all the large M.
Yes.
Right. However, what we are arguing is that because we've have this low rank structure built in, maybe we don't really need to do a backpropagation that goes through all the neurons.
Okay.
Because there is a lot of redundant information in U and V as it passes through the nonlinearity signal.
Okay. And also, like, on what basis, like, do you come to the conclusion that you need to sample some selected 4 or 5 rows, like, depending?
Okay, that's a very, very good question. So you can simply try this. So if you take a random matrix and take the SVD and say you take a matrix like this with orthogonal columns.
Yes.
You randomly sample some coefficients.
Right.
And then you try to collect those samples after you pass the sigma, like a scalar nonlinearity sigma.
Right.
And if you collect the outputs, in many cases, if the sigma is a very nice function, like a tan H function, then the output, if you collect them and then if you take the SVD, you'll realize that they lie in a lower rank space.
Oh, okay.
Then because the output is also low rank, it means that you don't really need to know all the neurons, all the hidden states to infer where it is in this low dimensional space the output is. If that makes sense.
So you don't need any information from the physical problem that you're solving. Like, for instance, if it's a fluid problem or if it's like a Helmholtz problem, like what you showed before, I don't think any of that really influences your decision of sampling these rows from your.
It does implicitly.
Okay.
Maybe not directly,
Right.
but you are learning the basis parameters. So U and V is learned from the physical problem,
Right.
right? So indirectly, I think it is influenced by your physical problem.
Okay.
After it is learned, well, the subsampling itself is completely dependent on the weight matrix that you've learned.
Okay.
It doesn't depend on the problem the algorithm for subselecting these rows does not depend on your physical problem.
Okay.
Not
Thank you.
directly, yes,
Thank
if
you.
that was what you're asking.
Yes, I think that's exactly what I was. Thank you.
Okay. All right. These are
So I have a question here. So mu is a physical parameter, right? So during the rank reduction part, what kind of physical information we are losing? Because I think when we are reducing the rank, some information will be lost. So what kind of information will be lost?
That's a great question. So yes, so the mu's, they come in through this coefficient and the diagonal, coefficient parameters on the diagonal of this previous matrix, right? So what you would like is the physical parameter belongs to some physical parameter domain D, right? So you'd like this compression to be valid for the range of physical domain D. So in a way, you're building a compressed version that is approximating the large neural network, right? So you would like that this approximating this to be similar, to be accurate when for your parameter range mu.
Yeah. Okay.
Yeah. So if you, for example, allow this S sub L to be, the coefficient parameters to be completely unbounded, then maybe this approximation will only hold for a local part of the range of S for all the unbounded range. But if you're really only interested in the physical parameter domain, so that restricts the coefficients here to be in a certain range. And you're really only building a compression that's valid only at that range. So the physical parameter range is important. We do take that into account.
Okay, good. Thanks.
Okay. Yes, but all of this, having done so, what you're really doing is you're taking sort of contiguous layers, given this function, you're approximating it with this smaller neural network with v hat and u hat in place of v and u. And this sort of a technique is in the field of model reduction, this technique is very standard. And it's empirical interpolation or discrete empirical interpolation is bread and butter of model reduction. So it's not a completely new technique. This subsampling idea is also not new, but we've applied it to this setting, which I think is and it also goes beyond subsampling. There are other strategies for exploiting this low rankness. However, we are applying it to the neural network, which we thought was very natural to do. But you, of course, need a neural network that has this low rank structure for this to work. Okay, now if you backpropagate to this smaller neural network, smaller low rank neural representation that we call a fast learner, then the fast learner backpropagation has the complexity that scales with these smaller weight matrices. So it's an order of, has the complexity layer times r hat times r, where r hat is maybe the maximum of r hat L for all of the layers. And now you have sort of decoupled this backpropagation complexity from the large complexity M from your original network. So this backpropagation for this learner, regular learner, is expensive, maybe cheaper than a larger network that's dense and full rank, but still expensive, depends on capital M. The fast learner, the backpropagation is now decoupled. And it only really depends on R hat and R. And if you assume that R hat scales closer to R, then your backpropagation will be really fast. Okay, so for example, if you use the subsampling strategy and if you use empirical interpolation, what you're really doing is you're building a IM basis functions psi of L, and you have some sampling matrix P sub L. And then, the IM and DIME has this form where you replace this V, VL plus 1, for example, by, VL, and you have this psi L PL transpose psi L inverse, and this is what allows you to pick off the coefficients in the IM basis for the output of this sigma of this nonlinearity by really only looking at a few entries. So you could take you can view this as one method of compressing your V and U to V hat and U hat by writing it as this matrix and this matrix. And since this is a subsampling matrix, you're really only keeping a few of the rows. And this is a permutation matrix that picks up only, it's a few columns of the permutation matrix. So you're picking off only a few rows. And then, you solve the system to pick off the coefficients. And then you project back to V anyway, which is low rank. So this, if you calculate out this matrix, then you get a smaller matrix V hat. This is, very standard procedure in model reduction. Okay, so now we can derive what's called the fast phase. So instead of doing the fine-tuning phase, where the backpropagation operation scales with the width, we can plug in this FastLRNR, where the FastLRNR you had is the smaller architecture that we derived in the previous slide. We can replace the pins loss. Instead of using the fine-tuning loss before, we use analogous pins loss for the FastLRNR, which has this compressed architecture. And we just solved this system. And another thing that I should mention is that, okay, now the neural network is really, really small, which means, and the number of coefficients S is also very, very small. It's small r times L, and our L is usually 5. So we have, depth 5 at most. So this is a very, very small dimensional problem. And so you really need to only solve it at a few sampling points in terms of your spatial or spatial temporal domain. So this summation over a few samples, the sample size is going to be also very small, as we will see. Okay, so far I've been kind of maybe telling you that this is sort of there's no problems at all, but okay, here is a sort of a limitation of this method, is that turns out if you do direct gradient minimization on this problem, it is not very stable. So what we do is, okay, maybe don't look too far. We say that the hypernetwork gives you a good enough guess. Don't venture out too far beyond what's the coefficient parameter space that's given by the hypernetwork output. And so we put a localization regularization so that it doesn't leave the neighborhood too far. So what typically happens is that first, if you don't include this localization loss, you do get an initial decrease in the pins loss, but this fast version of the pins loss, however, it diverges after a while, and that's not good. Sorry, I should correct that. The fast version of pins loss continues to go down, but the generalization error, the actual true accuracy, the test accuracy, goes down and then peaks up. So it is a unstable minimization problem in that sense. However, this gradient descent applied to this loss is much faster. Okay, I'll give you a numerical example. It's a very simple numerical example where it's a convection diffusion reaction problem with 3 physical parameters. So mu1 controls the convection speed, mu2 controls the size, is the coefficient of the diffusion term, and mu3 is the coefficient for the reaction term. And we consider, 2 parameter domains. One is just pure convection, where, your linear convection speed is changing. And we also try, another parameter domain range where, you have all the effects from diffusion and reaction. So for the first problem, we say maybe mu1 goes from 5 to 8. And in the second example, we look at maybe the convection speed goes from 1 to 3, but then diffusion can vary from 0 to 2, and also the reaction term can go from 0 to 2. And now during the meta-learning phase, you monitor the test error, and then you try to pick the right parameters for lambda sparse. If you recall, lambda sparse is the term multiplying the sparsity promoting regularization term. And we kind of see this typical behavior for hyperparameter selection, where the regularization term, the regularization coefficient kind of start hurting the performance of the optimization at some point. And that's the one we take. So we try to make it as sparse as possible without hurting the approximation power of your neural network. Okay, and once we do that, we see that, okay, after the machine learning and the meta-learning phase, if we look at the hyperparameter outputs, which is mapping the physical parameters to the diagonal terms, we see that indeed the sparsity promoting procedure sort of worked. So for the convection example, we see that, okay, if you output the outputs of the hypernetwork, we see that there's really only a few non-zero terms. They're either zero or have most of them are zero. So you can, if you kind of remove all the zero outputs from your hypernetwork, you see that your lower rank neural representation really only has 10 or so dimensions. So for each of the layers, you have 10 dimensional weight matrices, and so maybe collectively you get 30 to 40 dimensional learner representation. And we pick the fast learner, which is the compressed version of learner. We construct those to be accurate at a few sampling points. So for example, we pick 12 sampling points that are uniformly spaced. And this is we're comparing the fast learner versus the learner. And you'll see that this compression doesn't come for free. So if you pick these 12 sampling points to be uniformly spaced, and construct a compression, they're going to be only accurate at these sampling points across parameter, which is an important point, I think. If you plot what FastLearner looks like over the entire domain, it looks like this. And as you see, the true learner solution for the convection problem has, it's just going through straight line characteristics. So it is constant along these straight lines. However, FastLearner is not really accurate in the entire spatial temporal domain. It's really only accurate at these points. If you compare these two on a log scale plot, you see that they're accurate to a certain accuracy, maybe 10 to the minus 2 and 10 to the minus 3, add exactly these red crosses where we've made the fast learner to be accurate. But, away from there, we don't really know. The accuracy is not very good. And as you increase the R-hat dimension, you, of course, get better agreements, both for U and, spatial derivatives and the temporal derivative U. But of course, you do not want your R-hat to grow too far. So all of this is predicated on the expectation that R-hat can be chosen to be small. Okay, so if you use this instead of, you use this fast learner instead of learner, starting from the initial guess that's coming out of the hypernetwork, you see that, okay, given an initial guess here, your L1 relative error as you do gradient descent, it always gets better for the fine-tuning phase if you use the full learner. And for this fast learner, it doesn't really get to the accuracy as it's not going to be as accurate as plugging the learner back into your PDE and doing gradient descent. However, it gets there much faster. So I believe the one epoch with Atom with FastLRNR is 0.004 seconds, whereas on the large learner where M, I believe, was something very big, like 4,000. And so the difference between these two is the wall time gain that you get. So although it's doing the same number of 400 epochs on the pins loss, if you do the fast phase, then you are at this accuracy much faster within a fraction of a second. Whereas if you use the standard fine-tuning phase with the full learner, then it takes more time because you have to. I mean, I guess you do get some savings compared to the full pins or the vanilla pins because you have learned part of the parameters already, and you have a smaller dimensional unknowns to back out from your pins training. But if you use fast phase, it's a lot faster. And in some instances, the gain you get is not very significant, and it's however you do get it much faster. So what this is telling you is that there is some kind of a gradient descent flow that even just using the FastLRNR, which is the small compressed network, that will improve your solution. However, it is the gradient flow, as I mentioned earlier, is a bit unstable. So there is still a question of how do we stabilize this? What are the best methods for training this FastLRNR during the fast phase? Okay, so I believe that concludes the numerical part of the talk, and I think we are already at 1 p.m. I believe in Eastern time. Ameya, can I continue a little further, or
yes, please take your time.
Okay, so I'll try to cover the theory. But before we go there, any questions about the numerical portion?
Professor, I have a question on the sampling that you discussed previously. So
Yes.
you had mentioned about the sampling to be like more on the structured way that you have done on the slide. So is it forcefully meant to be like that, or are you saying that it can also be an unstructured sampling if you want?
Oh yeah, we took the uniform sampling for simplicity.
Simplicity. Okay.
Yeah, it doesn't, of course, doesn't have to be, and it's probably suboptimal. So that's another big question is, okay, how do you best select the sampling points?
Right.
Yeah. I mean, we wish we could formulate a learning problem that finds the best sampling points. But the short answer is we don't know yet. And how you pick the sampling points, I believe, is going to be important.
Right. Thank you.
Mm-hmm. Any other questions? Okay, so let me get to the sort of a theoretical motivation for studying learners. And it comes from a model reduction. So let me give you like a one-slider for introducing what reduced basis methods do. Is reduced basis methods proceeds in two phases, an offline phase and an online phase. And during the offline phase, what you try to do is you try to find a low-dimensional linear representation of the solution manifold. So if you have a parameter-dependent solution to some PPDE, then you try to find reduced spaces psi, which can represent all of the solutions, parameter-dependent solutions mu with uniform accuracy. And then you're saying that, okay, these reduced spaces, if you pick the right coefficients, you can always approximate u sub mu. That is the assumption of linear reduced basis models. And then if you can do that, then you can plug this form of your solution, which is a low dimensional because you expect the number of reduced spaces to be small. You can plug this into your residual and minimize the residual, and you get to do a fast solve. And this solve will, since it only depends on R parameters, the expectation is that you're able to do this low dimensional solve with a complexity that scales with the polynomial of R, for example. And after that, you try to compute the quantity of interest or QIM map by looking at some interested bounded linear functional applied to the solution you had of mu. And so the fast solve and the computation of the quantity of interest. So these are, what's done during the online phase. During the offline phase, you do the expensive work of calculating the reduced spaces psi. And of course, there are, machine learning data-driven methods that, tries not to do all of this and do something non-intrusive or data-driven, where you try to find a regression map that approximates the quantity of interest, this QI map, directly. Okay. And of course, this assumption is it is connected to what's called Kolmogorov N-width. And the Kolmogorov N-width is the approximation, the uniform approximation error that you can achieve using the best basis function that you can find, is psi I, of dimension R. So suppose here in the N-width, of course, it's the small n corresponds to this R. So suppose you can find the best reduced spaces to represent your solution manifold for all your parameters dependent solutions. So you pick the best species, and then you look at the uniform error you get if you can pick out the best coefficients, the C, to approximate a parameter dependent solution U. So this is the best uniform error you can hope to achieve using the best reduced spaces method. So many of the model reduction techniques, the classical linear reduced models, the assumption is that this D sub n, the Kolmogorov N-width decays exponentially, so that you can choose this your R, the number of reduced spaces, to scale with the log of epsilon, where epsilon is your desired uniform error. Now, if you compare this situation with the full order models, then if you have a prime Mertz system and you have a desired error delta, then and you want a uniform error bound delta for parameterized system mu, what you have is typically a capital N scales with the error to the power of 1 minus 1 over gamma, where gamma is convergence order of your method. If you have a or second order, third order, fourth order method, this is the kind of error guarantee you get. So what this is saying is that if you have an object like this on the right-hand side that scales with the error this way, then this number of basis functions you need, capital N, is going to be very large. If it scales like this, log of epsilon or such, then the number of bases you need, this small r, can be very small. And this exponential decay is crucial to the success of the reduced basis methods. However, if you look at a problem with convective effects, then you can easily show that even for simplest hyperbolic problems like the advection equation, the Kolmogorov N-width for these collections of functions is actually quite big and doesn't decay quite nicely or exponentially. So here we're going to treat time as a parameter mu. So if you look at the advection equation where this jump is coming in traveling to the right, this parameter mu we're going to treat the time t as a parameter. So you have a collection of functions, a spatial 1D spatial functions where the jump is just moving from the left to the right, and the Kolmogorov width has this sort of a lower bound, n to the minus half. So this means that your R is going to be, roughly, your reduced dimension you need is going to be epsilon to the power minus 2, so you need a lot of basis functions in the same order of finite element methods. So if the number of reduced basis functions you need to represent your solution accurately, if it behaves like the number of finite element basis functions you need for solving the PDE accurately, that means that you might as well stick to the finite element methods and not use the reduced basis method, because it's going to take about the same time. Of course, there may be some settings where reduced basis method still is useful, but yeah, you don't get the complexity savings. If your solution is a little smoother, instead of having a jump, if there's a jump in the derivative or the second derivative, you do get something a little better, but the decay rate still behaves like n to the minus alpha, where alpha is, I believe it's called a cutoff. I think this is like 3/2 and 5/2. So it still behaves like the finite element method. Okay, so what was introduced earlier to overcome this limitation with reduced basis method is the idea of transported subspaces. If you look at the advection equation, it looks like the initial condition is just being translated to the right. And it seems like your initial condition is fixed, and then you're just modifying the input x minus t, and this x minus t, if you write it in a separated form, this is the identity function of x, which corresponds to this x. And this t times, constant function of x, which is 1 over x, then it looks like it's a linear combination of two spatial functions. So the identity and the constant function. So it seems like although this object cannot be represented with a few basis functions, it seems like if you compose two, this is one spatial function, this is a linear combination of two spatial functions, it seems like you can represent this very efficiently. So what we did is, okay, instead of using one basis function, use two basis functions, one for modifying the input variable, and then one for representing the profile of the waves, let's say. So you have one basis function phi, another basis function psi, and then you take a member of these, and then you compose them together. There is a minus here because naturally when you do method of characteristics, you have to trace your characteristics back. So there is a spatial inverse here, and this was introduced for spatially one-dimensional problem. So you can take a one-dimensional spatial inverse. And we show that you can plug this ansatz into your reduced model, and the cost for updating the basis is still polynomial of R, which is the reduced dimension of which is the reduced dimension of both of these spaces. So we call this a transported subspace. Okay, so what do these spaces look like? So if you have, for example, two basis functions phi1 and phi2, the span of, if you take a span of these two basis functions, then you get functions that are shaped like this, but they're not really moving. So you can't really represent moving waves very well. So what you do is in addition, you do have another basis function representing the deformation of your space, of your spatial variables. And then so if you take a sample out of F composed with G inverse, where G is taken out of the span, then you can represent a profile that's also changing depending on this, but also traveling and being deformed also by this G, which is also a raw rank. And this object you can plug into a PDE, and you can do a fast solve that only scales with the dimension small r. Okay, so these previous examples, if you look at them, you can represent them very easily in using transported subspaces, because this one is just moving through a space, a smooth curve, one profile moving through a smooth curve. Here, this profile is being dilated, but this dilation you can also represent in an efficient way using transported subspaces. Okay, so let me, that's the basic idea. And so if you kind of look at the model reduction literature and look at how, this encoding, fast solve, and computation of the QI map, if you look at the case where the Kolmogorov bandwidth is decaying quickly, these RBM methods, they satisfy all the computation of the fast solve, the encoding, and the QI map. All these computations are very, very efficient. However, if you look at the nonlinear analogs, nonlinear generalizations, this is not always true. So not all of the methods can encode your solution manifold approximately, accurately. Not all of them can be plugged into a PDE and compute a solution in FastSolve. There are a few methods that can do this, but most of them are able to encode the solution manifold accurately, but you cannot really plug them into a PDE and minimize the residual in a fast way. And just because you have the solution in the nonlinear case does not mean that you can compute the QI map efficiently. So in the linear reduced models, everything, if you can build a reduced basis method, it takes you very, very far. Whereas in the nonlinear extensions, you have to be careful. Just because you can encode the solution manifold accurately does not mean that you can solve the PDE efficiently. And even then, that does not mean that you can compute the quantity of interest efficiently either. So in the nonlinear case, there is all these hurdles, and we're hoping that our learner is able to do all of these efficiently. And another comment about the data-driven methods, okay, you can take the data-driven route, which is called the non-intrusive methods. However, it is well known that these deep learning models, they suffer from instabilities called adversarial examples. So there is also a pathology that's associated with those approaches as well. Okay, so what does a learner have to do with a transported subspace? Maybe this is probably the last slide where I will be able to explain something to the audience. So before I get to the final theorem that I'll show you, this is what connects the transported subspace to the learner architecture. And that's what motivated us to look into this architecture in the first place. So suppose the f in the transported subspace is a piecewise constant function. This rho is a jump function. Then you can write it as a superposition of jump functions that's located in x of I. So these x of i's are these breakpoints, and so you have this piecewise constant function. If you compose it with a transport map G, this f composed with G inverse, then because this is a piecewise constant function, this G can be moved to the breakpoint x of I. So you get rid of this inverse operation you have to worry about. It moves to this G of x of I. So it's just moving the breakpoint. So if you want to take this f and apply G inverse, f composed with G inverse is where instead of worrying about anything, you just need to move the location of this breakpoint from x of I to G of x of I. And if you stare at this for a little bit, it looks very much like a neural network. Here is a nonlinear activation function. There's a previous layer where this G is acting on the bias, and you have these weight functions B. So if you compare with the two-layer learner H of X, if you look at these, if F and G belong to a low-dimensional space, a low-rank space, linear space, then this beta sub I will be a low-dimensional vector. And this G applied to X sub I can be also represented in a low-dimensional way. So now you're looking at something that's very close to a learner where the weight matrices belong to a low-dimensional space, a space that has a linear space with a low dimensionality. And then that's where learners come from. And so, okay, so let me, since we're sort of out of time, let me get to the final theorem, that the theoretical result that we have. Okay, so if you have one profile that's moving through some straightforward characteristics, like the convection problem, where everything is moving following the characteristic curves, and the characteristic curves themselves have a low-rank structure, then the transported subspace does a good job. However, if you look at the solution of the Burger's equation, this is the solution of the Burger's equation, where this is a spatial variable and this is the scaled time variable. And so if you start out with an initial condition that looks like this, it's a nonlinear equation where, if you have a decreasing portion, that's going to develop into a shock. And these shocks are going to propagate at nonlinear speeds that depends on the time, and they're going to merge. And then there is a rarefaction wave that can start if you have an increasing portion, entropy violating shock, if you will. And then you get, and these rarefaction waves, as they merge with shock, also affects the speed at which the shock moves. So you might ask, the question that we had was, okay, transported subspaces is useful for nice problems, but if you have a shock interacting, what is the low dimensional structure that you can exploit for this case? And I always sort of ask the audience this and wait a few minutes if they have any ideas. So I'll give you like 1 minute or 30 seconds. Can you guess what the low rank structure or low dimensional structure of this wave propagation is? Well, it took us a while, but it's the learner reveals the learner approximation reveals a low rank structure. So, for example, if you have an initial value problem of this structure, a scalar conservation law, let me jump to our theorem because I'm running out of time. So if you take a learner H of R, again, this is the learner that we were discussing in the beginning with rank equal to 2 and depth equal to 5, then any initial value problem solution with any initial condition U0, you can approximate over time with the learner of rank equal to 2 and L equal to 5 arbitrarily well. The width can be very, very large, but here the rank and depth are fixed. So there is an efficient representation using learners, or no matter how many shocks you have that are colliding, how many rarefactions that you have, this is efficiently represented by low-rank neural representations. So this is the reason why we try to use a learner to fit wave propagation problems. So this is sort of the structure of the approximations, and they have like this low-rank compositional low-rankness. So we were able to derive a new form of the solution to the entropy, the new solution formula for the entropy solution, and it has exactly the type of structure that resembles a learner architecture. And let me finish by commenting a little bit on the so-called Kolmogorov barrier. So many engineers refer to this slow Kolmogorov decay width as the Kolmogorov barrier. And I spent a long time wondering where the barrier is. So I mean, when people mention the barrier, you would think that okay, maybe there is maybe there is a wall, or maybe there is a singularity somewhere, and you wonder, okay, is it proper to refer to this slow decay as a Kolmogorov barrier? But it is very the terminology has caught on, and many people refer to this as a Kolmogorov barrier. However, this learner result got me thinking. So if you kind of look at if the horizontal axis is sort of the depth of the learner network, and if you kind of think of the space of functions that learners can approximate with a given depth, it seems that if you fix all the inner layers and leave only the final out layer variable, then maybe that corresponds to a learner of width L3/2, maybe something sitting between 1 layer and 2 layers. And so the Kolmogorov barrier, sort of metaphorically speaking, or very roughly speaking, sits here. And transported subspace, which is roughly equivalent to learner of depth 2, is where this is. And as I mentioned in the previous slide, if you have 5 layers, it seems that we can approximate, shock interactions and entropy solutions, essentially. And all of this is sort of bound by what we call the entropy barrier, which has to do with the computation of the QMI map. So it seems that the learner is able to overcome this Kolmogorov barrier, and we've shown that theoretically, and I hope we can provide a computational framework for doing this. So that's the end of the talk. I know it was a lot, so please feel free to ask questions. The FastLRNR paper just appeared, and the meta-learning framework was introduced in the Zurich's paper. And these two are theoretical results. And of course, we were working on, data-driven methods for learner during the meta-learning phase, so that we don't have to rely on solving the PDE. We can use existing numerical methods to provide the data. And we're also looking at other fast algorithms during the fast phase, because we know that the pins loss minimization, although it's a very elegant way of solving the problem, is still unstable. So we need to stabilize it. Okay, so thank you for your attention.
With that,
thank you, Professor, for an elaborate and informative talk. So you did mention about transforming basis, if I'm not wrong. So does the theory, theoretically, what you suggest is that instead of manually or just picking appropriate basis to solve your problem, it's as good as having an LRNR with a total number of layers of 5 and width. No, depth of 2 and width of 5. Am I right to say that? Or
yeah, that's right. So instead of trying to, so it's saying that, okay, what is the low dimensional structure here? And the transported subspace is so sort of it gives you sort of a hint right? So if you have a solution that's really nice like this, where there's no shocks,
Yeah.
everything is transporting nicely, then you just need the transported subspace and you're done. However, it's clear that that doesn't work for this kind of a problem. And what we are showing theoretically is that if you take a learner with 5 layers, which is just you're kind of extending the transported subspace by adding more layers. The transported subspace kind of corresponds to a 2-layer learner.
Yeah.
And then to have these complicated interactions, you need 5 layers. And you're right. In this theorem, we manually construct everything, right? Because it's just a theoretical construction.
Right.
But this gives us hope that, okay, maybe if you plug in this in a learning problem, like our meta learning problem,
Yep.
maybe you just need depth 5.
Yes. Okay. So I think it's almost like analogous to saying like I think you had like I think recently you had like Kolmogorov approximation theorem, just like the universal approximation theorem for general MLPs. I think this kind of makes it analogous to that for rather but this is more like in a physics setup. Is that right? I don't know if it's like
So it's a
yeah.
theoretical setup. I guess like if you're mentioning like the Kolmogorov superposition theorem.
Yeah, I was just referring to the Kahn network, the theorem.
Yeah, that's
Yeah,
right.
yeah,
So the
yeah.
Kahn network says that, okay, I mean, it's a very old theorem,
Right.
right?
Yes.
Where if you can, make a very, very nice representation of there's the inner layer, right?
Yep.
And then if you combine these functions, there's an existence theorem.
Yes.
It's kind of like that. Yes, this is a sort of an existence theorem, if you will.
Okay. Okay.
Although one difference between, I know that superposition theorem, it involves very complicated functions that you can never hope to really construct
I believe they are referring to spline bases, if I'm not wrong. Like I think they are by and large referring to spline bases.
Yes.
Problem.
But the Khan is inspired by superposition.